Good morning. I'm glad to have you here as we discuss today the topic of equivalent resistance. So equivalence is actually a super commonly used tool in all of circuits analysis, right? And so before we start talking about equivalent resistance particularly, I wanted to start with a little bit more broad discussion of what we mean by two things being electrically equivalent, okay? And it actually has a fairly simple definition. Two networks are electrically equivalent, and I really should kind of specify two-terminal networks are electrically equivalent to each other if they have the same voltage-current relationship at the two terminals, okay? So by way of kind of showing a quick example of this, I'm showing here two different networks, and the exact relationship or kind of construction of these two networks isn't really the main point. I'm just showing you that you can have two different networks. I just sort of randomly drew one style and then another style. I could have drawn just about anything here for the point that I'm trying to make. What I'm basically going to show you here is if I imagine taking, let's say, a voltage source, right? Little ideal voltage source, and putting that ideal voltage source across network 1. Let me just call that, I'll just say that it's got a voltage of V that I'm putting across that network. And as a result of that V that I'm putting across that network, and let me actually name this a little bit better. Let me say this is V applied, right? That's like an applied voltage that I'm sticking across that network. And as a result of that V applied, there is a resulting current. Okay, so I'll name that I resulting. Okay, so the voltage is causing there to be a current that flows in network 1. Well, network 1 is equivalent to network 2 if I take that same voltage, that V applied, and I put it over here now on this network, right, V applied, and for any value of that V applied that I put on there. So I can choose any value for that thing, but if I put the same value across the network 2 over there, and when I do that, it results in the same current, right, regardless of what V I put on there, right? So for any V applied, this relationship holds that the I resulting will be the same between these two networks. That means network 1 is equivalent to network 2. Does that make sense? Now, you might be wondering why I showed another pair of these networks up here. The reason I'm showing the other pair of these networks is it actually works the other way too, where instead of thinking about V as being sort of the cause and I being the effect, right? Like you put the V across the terminals and the current, the voltage across the terminals and the current is the effect that happens. We can think of it the other way too. What if we were to put a current across these terminals or through these terminals, right? So think of a current source, and we put that through these terminals, and I could call that maybe I applied, right? And as a result of that applied current that I put through these terminals, we start seeing a voltage across the terminals, right? So maybe I'll call that V resulting, okay? These two networks are electrically equivalent to each other if we essentially meet the same requirement, right? I put that same I applied over here on this network, and as a result of that applied current, we see the same voltage at these two terminals, okay? If this happens, then network 1 is equivalent to network 2, okay? They really say the same thing. I'm just trying to point out that we generally are either thinking of there being a voltage that's a cause of current flowing, but we can also think of it backwards from that, that if we induce a current in something, that will cause a voltage also, right? So if we can kind of think of that either way, is my only point. Okay? Now, once we have determined that two networks are electrically equivalent to each other, what we can say then from there is that when we hook that network up to other circuitry, right, it doesn't matter which of the two equivalent networks we hook up to the other circuitry, the behavior as seen at the two terminals ends up being the same. Okay? So what I've got shown right here is imagine I take network 2 and I hook it up to some circuitry. I take network 1 and I hook it up to the same circuitry, what we're going to find is that the voltage and the current that you see at the two terminals will be the same regardless of if you hook up network 2 or if you hook up network 1, because we've seen that network 2 is electrically equivalent to network 1. Okay? So basically what we can say there is whatever voltage we have here is going to be the same voltage we have here. Those will be the same, right? Or whatever current that we have flowing here is going to be the same current that we're having flow right here, because the given circuit there is not changing between case 1 and case 2. We're just hooking up two different networks to those two terminals, and as it sees it at the terminals, there's no difference in what the given circuit sees for network 1 versus network 2 applied to those two terminals. Does that kind of make sense? So if you were just kind of trying to view what's going on over there with network 1 or with network 2 from the viewpoint of the given circuit, you wouldn't be able to distinguish between the two of them by just looking at what's going on the connection terminals. Does that make sense? All right, so that is sort of a bigger discussion of what we mean by equivalent circuitry, right? Now let's get into what do we mean by equivalent resistance. Okay? So this is pretty handy, that basically no matter how big of a resistor network we might be looking at, let's say we've got a bunch of resistors that are connected all together in some kind of a network. However many of those we have and however complicated it might look, that resistor network is reducible down to just one resistance value. Like just replace it with just one resistor, and as long as you choose the correct value, that one resistor is going to be electrically equivalent to that big old resistor network, right? So that's a very handy thing for us to be able to do. And that's what we're going to start learning some rules to be able to do that kind of equivalent resistance evaluation. Okay, so that's kind of where we're going with this. There are two big sort of constructs as far as how resistors might actually all be connected with each other. And the first one we're going to look at is when resistors are connected in series with one another. So in series basically means, you know, you've got the two terminals of one resistor, one of those terminals connects to another resistor, then another resistor connects to the other one of those terminals, and you sort of chain them together in series, right? So that's what the idea is of series here. And my question is, can we figure out what the equivalent resistance is of n resistors in series? All right, so however many we want to use there, but you know, some arbitrary number of resistors that are in series with each other, can we figure out what that equivalent resistance is going to be? Good news is, yes, we can do that. All we need are Ohm's law and one of Kirchhoff's laws. Okay, so we're going to start seeing if we can do that. Let me go ahead and start with this circuit. And I guess really the first place to start is we want to actually make it a circuit instead of just this little chain of resistors. And so what I propose is let's actually excite this little network of resistors with a voltage source that we choose. Okay, does that sound good? So really what I'm going to suggest here, why don't I take a voltage source and I'm going to call it Vs, and I'm going to imagine hooking this Vs up into that chain of resistors right there. And if we're going to have an equivalent resistance, then it basically means that whatever current results from me hooking up that Vs right there, right? Let's say I have a current of I that flows as a result of hooking up my Vs. I'd better have, if these two resistor networks are equivalent, that means that if I hook a Vs up here, same voltage value, and then we hook that up into this just equivalent resistance, I'd better end up with the same I flowing in that case if Req is going to be equivalent to the combo of R1, R2, R3, R4, you know, et cetera, et cetera. Okay, so that's kind of the starting point. Now, let me actually assume we don't know much of anything about how this works just yet, and let's just say for any one of these resistors that I've got up here, I could identify the current flowing through each one of them, and let me label each one of those as like IR1. And here, let me call this IR2. Okay? For this over here, let me label that I4. for Rn. Those are the current values that are going through each one of those little resistors right there. Ohm's law tells us that if we have a current that flows through a resistor, that's going to cause there to be a voltage across the two terminals of the resistor. So let me also put those on there and name those as well. Let's say that, here for R1, I'm going to call that VR1. That's the little voltage that as a result of the current flowing through that resistor, that's the voltage that we're going to see across the terminals of that resistor, right? And I can do that for the other ones as well. For R2, I'm going to call that VR2, right? For Rn, let me call that VRN, okay? And those are being measured actually right up here on these connection points for these resistors. So far, so good, right? I mentioned we are going to be using Kirchhoff's voltage law, right? Well, we're perfectly set up now to be able to use Kirchhoff's voltage law for this big loop that represents this circuit, right? So we can do that by essentially going in here. Let's count voltage increases as negative and voltage decreases as positive, okay? We have to choose that whenever we get ready to do a Kirchhoff's voltage law analysis, kind of choose which direction we're going to take to be positive. So an increase, let's take that to be negative, and a decrease, let's take that to be positive. Okay? Why? Because I chose it. Okay? It doesn't really matter which way we do it as long as we're consistent. Okay? So for Vs right here, Vs, if we're going clockwise around this circuit this way, Vs actually represents an increase in voltage as you go around clockwise, right? Because you go from a negative to a positive. The power of choosing the kind of the direction that I'm assuming to be positive here is you can take whatever the value is of the terminal you first encounter as you go around this loop, and you can take that as the sign of that term. Right? So we first encounter the negative of the Vs. That means I can count this as a minus Vs. And by the way, I forgot to label this up here, but what we're about to do is a Kirchhoff's voltage law equation. Okay? So I'll have a minus Vs, then I come around up to R1, and what will I have there for the voltage across that? Plus VR1, right? So I'm going to put that in as plus VR1. And then I keep going through the rest of these, right? Plus VR2, plus, and let me just say it this way, dot, dot, dot. However many of those resistors there are, I can just keep on adding them up. They kind of have the same form for each one of them until I get to the last one, right? And the last one, let's say that's VRN. Now, that's a sum of voltages. What is that sum of voltages equal to? 0, because that's what Kirchhoff's voltage law says. All right, now here's a question. Can I replace VR1, VR2, so on and so forth, VRN, with something else? Okay, each one of those terms, I can apply Ohm's law to each one of those terms, right? And if I know that I've got VR1 here for R1, right, the other way of saying that is that that's going to just be equal to IR1 times R1. Agree with that? Okay, so let me just go through and replace all of those. I have minus Vs plus, okay, IR1 times R1 plus IR2 times R2 plus dot, 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 plus IRN times Rn. And that has to all equal 0. Now, let me ask you this. As we look at the current that flows around this loop, are there any kind of relationships that we can establish for all of these currents that we see going through these resistors? They're all the same. Why are they all the same? Because they're in series with one another. There is no other place for current to go, right? There is only one loop where current is flowing. So instead of calling these IR1, IR2, and IRN, I can go through and actually notice that each of these is just going to be equal to I. Right? The same I that I identified right at the beginning of the problem when I put my Vs across all of this. Okay? So if all of those are I, what that means is I can, let me do a couple things here. I'm going to move Vs to the other side of the equation, and I'm going to factor out all of my I terms. Like this is going to be equal to Vs. Do you agree with that? Okay. Furthermore, if I would like, I could divide both sides, and I'll just do this, you know, I know this annoys some people, but I'll just divide both sides by I, like that. Okay? That is the ratio of the applied voltage to the resulting current for that circuit. Okay? Now here's my question. What would that be if I was, instead of doing it for the upper circuit up here, what would that look like if I was doing a similar thing for the lower circuit? It's much simpler, right? What would that look like? Req is, by definition, just Vs over I, and you will notice Vs over I is the same Vs over I in each of these cases, right? So that tells me that my equivalent resistance that I'm dealing with here is just going to be equal to the sum of all those resistor values. Now, I would assume that actually most of you knew that already. R1 plus R2 plus ... plus Rn. So one of the points of me doing it out this way is to show you that it really arises out of a combination of Ohm's law and one of Kirchhoff's laws. That's where the concept of equivalent resistance, you know, for series circuit, where you just add them all together, it comes out of a Kirchhoff's law. Okay? Now, I want to also show it this way too, because, you know, this is nice, but I want to show it in another format as well that's a little bit more palatable in terms of kind of math notation, right? In terms of math notation, you can do this same thing by using summation notation for some index. I'll just use the letter k equal 1 to n of just r sub k for however many elements that you've got being n. Okay? And all of this is set up for series resistors. All right? That makes sense? Okay, let's move on and look at resistors in parallel now. Okay? For resistors in parallel, we're going to use a similar kind of strategy, right? Let's go ahead and excite both of the circuits with some kind of a voltage that we call Vs. Okay? And if we're exciting this circuit with a voltage of Vs, let's excite the other one with the same voltage. Okay? Both of those are Vs. As a result of that Vs, in each case, we're going to have a particular current flowing, I, and if these are going to be equivalent, right, the resistor networks for each of these circuits, if that's going to be equivalent, then the I had better be the same in each of these cases for the same amount of voltage that's being applied, Vs, right? So let me go ahead and also do the other part of this, and that is, let's go ahead and identify the voltages and currents that we're going to have for each of the resistors, right? So let's just label those as, this is IR1. Let's call this IR2. And over here, let me call that IRN. Okay, because I've got those currents flowing across those resistors, I also have voltages that are seen across the terminals of each one of those, and I'll label those this way. Let me call that VR1. Here I'll call this VR2, the voltage across that resistor. And over here I'm going to call this VRN. All right. Now, in this case, probably the best thing to use in terms of one of Kirchhoff's laws is not Kirchhoff's voltage law, but rather Kirchhoff's current law. Okay, so let me label that right here, Kirchhoff's current law. And what I want to do is see if we can identify any kind of a relationship for one of the nodes, right? Let me identify the node that I want to look at. Let's say we look at this node right up here, okay? And I know that's a node because I can, you know, highlight across that entire wire right there without crossing any one of my circuit elements. I can keep on highlighting until I've got all of that stuff drawn on, right? So that's all one node up there. And anytime you apply Kirchhoff's current law, you do that at a node. So I'm going to do this for that node right up there. And let me identify positive values as actually being currents that leave the node. Okay? So what would I write if I wanted to do a Kirchhoff's current law equation for that upper node? Current's leaving or positive, that's how I'm going to write it, okay? So I is actually entering. So how would I write that one? Minus I. All the other ones are leaving, right? Plus I R1 plus I R2 plus dot, 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 plus I Rn. And because this is a Kirchhoff's current law, what do I set all this equal to? 0. That means basically there's nowhere else that current is allowed to go. All right, now here's my question on this one. Do we have any kind of a relationship that would allow us to replace each one of these current values with a voltage value instead? Yeah, so we basically know Ohm's law. We can rearrange it and say that I has to be equal to V over R, right? So I can rewrite this thing, minus I plus V R1 over R1 plus V R2 over R2 plus dot, 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 plus V Rn over Rn. And that all has to be equal to 0. Now, are there any kind of relationships that we know for a circuit like this one where we only have 2 nodes, right? I identified the top node up there. The only other node that I have in this circuit is this bottom node, okay? If there's only 2 nodes, then there really can only be one voltage difference, right? Just the difference between those 2 nodes. And so no matter where I'm looking at, whether it be VR1, VR2, VRN, all of those nodes, or all of those voltages, I should say, had better have the same value because they are across the same 2 nodes, each one of them. Okay? So what can I do with VR1, VR2, and VRN and what I was just dealing with right here? Let me just call them all VS, because that's the same voltage, right, that we are exciting this whole circuit with. Make sense? That voltage source is actually holding those 2 voltages for the upper node relative to the lower node as VS. Okay? So now if I change all those for VS, let me also do this. Let me factor out VS additionally. Okay? So I'll do it this way. VS times 1 over R1 plus 1 over R2 plus dot, 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 plus 1 over Rn is going to be equal to I. Now, let me divide both sides by I and divide both sides by this sum. Okay, does that make sense? So on the left, I get VS over I, and on the right, I get 1 over R1 plus 1 over R2 plus dot, 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 plus 1 over Rn. Now, we already did this on the last example, but how do V and I relate for this little circuit up here where I have REQ? Same thing, right? VS over I is going to be equal to REQ, right? The VS over I have in this case is the same as the VS over I have in that case, and so that tells me that if I want to know what my REQ is, I can just take 1 over R1 plus 1 over R2 plus dot, 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 plus 1 over Rn for however many resistors that are all in parallel with one another. Okay? How would this be written if I wanted to write it in a little bit more sort of formal mathematical notation? Okay? I would write it like this. 1 over the sum, and I'll use k again as my index, right? K equals 1 to n. Now what would I write inside of that sum notation? 1 over Rk. Okay, so these are both valid ways that we can use to write this relationship. And just to kind of be clear over here, this is for resistors in parallel. Okay? All right, and again, I don't think this takes anyone by surprise. All of you are probably comfortable with this already, but I wanted you to see it from the standpoint of we don't have to take people's word for how this works. Kirchhoff's voltage and current laws, along with Ohm's law, can be used to prove to us that this is how equivalent resistance relationships work for series and then for parallel circuits. Okay? All right. Now I'm going to show you one little thing, and this I'm going to go ahead and label it clearly here as optional. All right? You don't need this because everything that you need to evaluate equivalent resistances for resistor networks in parallel, I already gave you with these relationships right here. But there is another format that is sometimes used when what you're working with are just two resistors that are in parallel with each other, right? So, trying to be clear, this is optional. You don't have to actually memorize anything here if you don't want to. But let's say here are my two resistors that are in parallel with one another. Our normal equation that we would use to find an equivalent resistance here for this little setup right here would be 1 over R1 plus 1 over R2. Well, would it be allowed for each of the fractions in the denominator of this thing, would it be allowed for me to multiply for the first fraction, multiply it by R2 over R2? Right? In other words, 1 over, here I would have R2 over R1, R2. Right? I just basically multiplied that fraction by R2 over R2. Is that allowed? Okay. For the other one, let me multiply it by R1 over R1. That's what it would give me. Why do you think I might have wanted to do that? Now, those two terms have a common denominator. So that means I can just add these together, right? This just ends up being 1 over. Here we would have R2, plus R1 over R1, R2. And then someone over here said, then you can just flip it. That's right. This is, if we're taking the reciprocal of this, which is, 1 over all of that stuff, the same thing can be done by essentially just showing that equation as R1, R2 over R1 plus R2. A lot of people like this equation because it's pretty easy to remember, right? If you have just two resistors that are in parallel with one another, the equivalent resistance is the product of the two resistance values divided by the sum of the two resistance values. So some people find that to be easy to remember, maybe sometimes a little bit easier to type into a calculator, perhaps. I don't know if that's really true or not. But either way, it's another thing that you can use if you care to. Okay? Don't try to use this if you try to get more than two resistors. Right? You cannot extend this out and say, well, it's just the product of all three divided by the sum of all three if it's 3 or more. Right? So be careful with this. This is only good for two resistors. All right. One of the other reasons this is handy to be able to do equivalent resistances is that we can actually sequentially apply equivalent resistance techniques, and we can reduce what ends up being a pretty big resistor network that might have some series relationships and some parallel relationships. We can sequentially apply these reduction techniques until we get it down to perhaps even just one resistor. Okay? So what that might look like, here I'm doing this with, just with variable values, not with actual numbers, but what would the first step be if you wanted to take a network like this and start reducing it down? What would you do first? So some people say combine R4 with R5. What was kind of your thought process on that? Find things in series if you can find them, because those are usually the easiest ones to combine, right? Things that might be purely in series. If you've got them, go ahead and combine them. So this would become what? This would become a resistor R1, right? It would now go through R2. This would go over here and go through R3. Here this goes over, and we're going to replace this, these two resistors, R4 and R5, with just R4 plus R5. Right? That's this one resistor value right there that you just collapse now into R4 plus R5. Okay? Then what would you want to do? Okay? Now, they say, well, we've got some of these things now that are now in parallel, not in series. Let's combine those, right? So you basically looked at it and go, we don't have anything left in series to combine, so let's go ahead and combine the ones in parallel that we've got. Okay? So what you would find there is that this would become another equivalent circuit where we still have R1, but now we're going to replace those three resistor values, R2, R3, and R4 plus R5. Those three resistance values, I'm going to replace all of those with just one resistor. This one I'm going to leave alone with R1, and over here this resistance value is just going to be 1 over R2 plus 1 over R3 plus 1 over R4 plus R5. And that would be the value of that resistor right there. So each of these little circuits is equivalent at its terminals, right, with the last one. So far, so good? Are there any more reductions we can do on this circuit? I can now combine R1 with this other resistor over here and make something where, I tell you what, I'll just call it REQ. That's the equivalent resistance of the original network, where I've got it all reduced to just one number. What is REQ going to be? R1 plus this big fraction, someone says. That's exactly right. 1 over R2 plus 1 over R3 plus 1 over R4 plus R5. Okay? Now, a lot of times you'll be given problems like this and you won't be doing it in terms of variables, you'll be doing it in terms of actual numbers. That tends to make it a little bit easier, but I wanted to do the first one to show you in terms of variables. That way you kind of see how it unfolded regardless of what the numbers were. All right, here's my last kind of important note before I do another example. We are not saying with any of today's lecture that you will always have resistor networks that are composed of resistors in series and resistors in parallel. It is possible to make resistor networks where resistors are neither in series nor in parallel, right? And therefore you can't use these, formulas that I've got for series and parallel. You can't use them on those because you don't have values that are actually in series or in parallel. And to kind of show you what this might look like, I gave you one common example. This is sometimes called a bridge circuit that I'm showing up here on the screen. Can you identify any resistors that are in series with each other in that circuit? Okay. I see a lot of people looking, trying to identify. Nope, there's not a single resistor that's in series with another resistor in that circuit. What about parallel? All right. Parallel means you better be connected, two elements better be connected across the same two nodes. So this one might be a little harder to see, so let me start coloring in my nodes. There's a couple of my nodes. Let's say here's another node right here, and then here's the last one down here. Do I have any circuit elements that are connected across a pair of the same two nodes? Okay, someone says R1 and R2. Looks like R1 connects from yellow to aqua, and R2 connects from yellow to green. Okay, so I would say you can look through this circuit as much as you want. You won't find any circuit elements that connect across the same two nodes. Okay, therefore, using our techniques I just showed you of series and parallel, I can't reduce that circuit any further. Okay, that's true. Let me tell you something else about it though. That does not mean it does not have an equivalent resistance. Okay, the rule that I gave you a little while ago that any resistor network can be reduced down to just a single resistance value, that still holds. It's just I can't use the tools that I showed you here to get there. Okay, so that's kind of the other thing I'm going to show you here. You can still take this and turn it into an REQ. That is still something you can do. You just can't do it by using the series and parallel rules that I just showed you. Okay, as a matter of fact, I'm not going to show you how to do this just yet. I'm going to leave that for when we start talking about Thevenin and Norton equivalence in a little while. All right, actually it's going to be several class periods from now. But I'll just go ahead and mention, as a little teaser for that, what we do is we go back to earlier principles, right? All the way earlier in the lecture, What I said is, if you apply a voltage and then look at the resulting current, you take the ratio of that voltage and current, that gives you the equivalent resistance. Okay? So that's what we're going to end up doing whenever I get to that and we start covering Thevenin and Norton. With me? We can just take a rain check on that, and we will get on with the example that we wanted to work today.